Hello everybody, and welcome to a new exciting video on EKF-based localization. Now, this is going to be the first part of two videos in which the first one we're going to talk about the known data assignment case, and in the second one we're going to relax this assumption. Now, first, a table of contents. First of all, I'm going to give an introduction of what localization is and some of the, I would say, taxonomy of localization problems. The second part, I'll talk about the main components that are required for a localization problem in terms of modeling and representation. The third part will be on landmark representation of how do we actually represent them in a known map. Then I'm going to talk about the motion model, and it's a probabilistic framework on how to capture the uncertainty in the robot commands in motion. Then I'll proceed to talk about the measurement model, which we're going to use a laser range sensor. In the final part, I'm going to talk about the EKF algorithm on how we are going to fuse all of these components together, and finally show the results applied to a fictitious map. Now first, what is localization? Well, basically, in simple terms, localization answers the question of where am I? So we have a certain mobile robot, or actually any type of robot. It could be a UAV, a UGV, or any type of maybe mobile manipulator. Now, the idea is that the robot is moving in a certain map and it has a knowledge of how the map looks, but it does not actually know where it is on this map. Now, this is actually a simple case of the more general SLAM problem, which is a simultaneous localization and mapping, where the robot does not know the map and it does not know where it is and has to do both at the same time. Now, basically, localization problems are categorized into three different problems. The first one is called tracking, the global localization problem, and the kidnapped robot problem. Now, the tracking problem is when we actually have a notion of where the initial position is. So we could say that we know to a certain degree of uncertainty that the robot starts at this point with this orientation. The global, on the other hand, means that we do not have any type of initial position knowledge, and we just have to, based on the measurements, to determine where the robot is in this known map. Now, the kidnapped robot problem is actually the quite most difficult one. In this case, the robot might be actually moving in a certain map, a known map, and it might have an idea of where it is at the moment. Okay, and the idea is that we just remove the robot from its position and throw it in another different position, completely blind. So this means that the robot actually thinks it is somewhere while it is somewhere else. Now, the kidnapped robot problem is actually quite useful for the cases of failure management. Okay, so if a robot's algorithm fails to localize the robot at a certain time, how can it actually recover from that failure? Now, there are actually several algorithms that could be used to solve the localization problem. We have the EKF, the extended Kalman filter, the unscented Kalman filter, the Markov formulation, and particle filters. Now, both the EKF and the UKF, they solve the tracking and the global problems. They are unable to tackle the kidnapped robot problem, while the Markov and particle filters can actually solve all of these problems together. Now we're going to discuss the main components or the basic ingredients to solve a localization problem or characterize a localization problem. Now, we need the following components to localize the robot in a known map. First, we need a representation of the map. Now, there are usually two types of representations. They are feature-based and location-based. Here, we're going to focus on a feature-based representation. The second is a motion model. There are usually two types as well, velocity motion model and the odometry model. In this case, we're going to use the velocity motion model. And finally, we need a measurement model. Now, this would have to be a range sensor in our case. And there's also the issue of data assignment. And we're going to talk a little bit more about this when the time comes. So first of all, we start with something we call landmark representation of how we present landmarks in a map. Now, a landmark is actually a type of feature that is used in a map. It has the following properties, you could say. Now, first of all, it must be reliably detected. So when a robot is in a certain position on the map, it should be able to detect this landmark, this unique landmark, really well and repeatedly. It should be unique, of course. It should be a point of significance. It could be, for example, vertices of polygonal obstacles. It could be certain features that could be extracted from a camera or any other type of features that's actually unique. And finally, they should sufficiently cover the map. So this would allow the robot to localize quite well in a map because, for example, if there are areas with low feature density or low landmark density, the robot would have a tough time trying to find or to localize itself in this map. So for example, now we have a certain robot that's moving in a map. That's the sensing range. This is a landmark right here. And once the landmark is in the sensing range, the robot will detect it, and the landmark is usually represented in this case as a vector with the x and y coordinates because we're dealing with a 2D case, and an index that represents this landmark. So this is landmark I. Now we're going to discuss the motion model, or how we actually represent the uncertainty in the robot motion and commands. Now, the velocity motion model is actually based on some simple kinematics for an omnidirectional or a differential drive, robot, and they are given by the following equation. We can see that the state at time k plus 1, which is comprised of the position, the xy positions, and the orientation, is equal to the previous state plus this term right here, which describes motion based on commands which are given by v, which is the linear velocity in the direction of the robot's motion, and omega, that is the rotational velocity around the z-axis. And of course, delta t is the time step. Now, this function will be called f, and it's a function of x, the state, u, the commands, and alpha. Now, of course, the v and the omega here are actually noisy commands. They are given by the nominal commands, the v and the omega, plus some Gaussian random variable with variance related to the magnitude of the original v's and omegas. So the bigger the required command in terms of rotational or linear velocities, the more variance we have in this noise. Now, gamma here is actually just a parameter that it has zero mean and a certain variance. This is used to describe error in the final rotation of the robot between two time steps. So now we're going to discuss a measurement model, which is simplified range sensor model. So now we are going to describe the measurement model. We have a robot with current state x, y, and theta. We attach to it a local reference frame with x local in the direction of the robot and y local perpendicular to it. This is the robot's sensing range. We have also two landmarks in the robot sensing range. That will be landmark I and landmark K, given by MI and MK respectively. Now, in this case, the robot will give us two measurements, Z1 and Z2. Now, Z1 will contain the distance to landmark I and its orientation with respect to the robot's local frame, and the same would apply to Z2. So Z1 will be given by this function, which is G of function of the landmark and the robot's state. Here we have the first component will be the distance between the robot's center and the landmark. The second component will be the angle, okay, between that is actually represented in the robot's local frame. It will be this angle right here. The same would apply to Z2, in which we have a function of MK and the robot's state. Now we're going to describe the EKF algorithm, in which we're going to put all of these components together. Now we're going, as we said, to discuss the EKF algorithm. Now I should mention that the EKF found here would be slightly different from the EKF algorithm that is found in certain settings. The main idea is that for global localization, we are going to have to keep track of certain or multiple hypothesis. Each hypothesis is actually made up of a plausible state, that is a candidate state that could be the current state of the robot at the time, and a corresponding weight that just describes how confident we are that this is actually the true state. Now, this is because in global localization, we usually don't have an idea where the robot starts, and hence we have to keep track of different plausible candidates, which will be filtered out later as we take more measurements. To this end, in global localization, the state density will be represented with a Gaussian mixture as opposed to a single Gaussian. Now, this would be given with the following form, which is the sum over n Gaussian mixtures of a weight, omega ki. Now, the superscript here would be usually reserved for a hypothesis index, unless I state otherwise. And then we have a Gaussian density with mean xki and covariance matrix pki. Now, of course, the sum of the weights should sum to 1 for this to be a correct PDF or probability density function. Now, a few remarks. Now, actually, at each time step, we might create new hypotheses. Now, will be actually the case in the unknown data assignment, which we will discuss in a later video. And of course, to keep the number of hypotheses limited, in case we just grow them at each time step, we have to utilize something we call pruning and capping. And sometimes we use something we call merging. So in pruning, we just get rid of the hypotheses that have extremely low weights below a certain threshold, and we just renormalize the weights. Capping also just keeps a number of the, for example, let's say first 10 or 20 highest weights. Merging will aim to mix some of the weights together to give us a Gaussian with a lower number of hypotheses. And a final note that is quite important in a numerical application of the algorithm. It's actually better to keep track of the logarithm of the weights. Now this will help us take care of the rounding of errors, because some weights can get extremely small, but we might still need to keep some of them for later, because some of these hypotheses might prove useful when the robot takes more measurements. So we usually keep the logarithm of the weights and not the weights. To describe in detail the flow diagram of the whole EKF algorithm. So first of all, each of these steps will be repeated for every single hypothesis I at each single time step k. So first, we start that we have from the previous time step, we have the hypothesis x bar k minus 1i and their corresponding weights. So first we perform the prediction. We get the x bar ki using the function f of the motion model. Of course, we assume that we don't have any idea of what the noise is, so we just update using the nominal commands. We also update the covariance matrix pki using the usual Kalman Kalman prediction step. Here we have the matrix gk and the matrix vk. These matrices are given here. Now gk would be the Jacobian of f with respect to the state evaluated at the previous state at the previous time step, and the current control commands, that is the current v and omega. The same would apply to v, but v is the Jacobian with respect to the input commands. Okay, so with respect to the v and the omegas. Now m here is actually just the covariance matrix of the input noise. So the basic idea of this is that we are using the Jacobians to transform the corresponding covariance matrices from the respective spaces to the current state space. That is the usual prediction step. We're going to just call it predict, and then we assume that at this current time step we observe m features. Now these features might be different. We might observe different number of features at each time step depending on how many landmarks exist in the current robot sensing range. So each feature will be represented by a ZG, okay, which is a a distance and an angle, and SG, which is the index of the landmark that we observed. So notice here that we assume that we actually have, okay, an SG, which is the association that tells us which landmark we observed. Now, this is not usually the case, and we relax this assumption in a later video. So now, what we do is that we first compute the predicted measurement for hypothesis I, okay, that we are going to use the function j, and it's going to take the landmark SG, okay, because as we said, we have the corresponding index of the landmark, and it's going to take the predicted state. We then compute the classical S and K matrices of the Kalman filter, and then we update the state mean using this equation here. Now this difference here is called the innovation, which is the difference between the real measurement and the predicted measurement. K is actually called the Kalman gain, and xk is actually, of course, the predicted state, or in this case, we're going to loop through this steps here, so xki would be, one updated from the previous measurement. And of course, we update the covariance matrix using the usual Kalman update. And finally, we compute something that we call the likelihood. Now, this likelihood is actually, in loose terms, it's actually the probability that there is actually, let's say, correlation between the current measurement and the predicted measurement. So it could come off as a probability that this measurement, the real measurement that we observed, ZG, was actually generated by the landmark SG. Okay, so this is actually computes how correlated these two are, or how correct our assignment is. Okay, but in this case, we assume that we have full knowledge of the assignments. So in this case, we just compute it because we're going to use it in the weight updates. Now, of course, the H is the usual Jacobian of the measurement function with respect to the state, evaluated at the current predicted state and at the landmark SG. I should note that these xki and the pki are actually looped through this repetition for the various features. So this is actually equivalent to us receiving several independent measurements and just updating them sequentially without any prediction. So after we finish this, we actually also update the weight of the hypothesis based on the previous weight and the product of all measurement likelihoods. So this would mean that the hypothesis, okay, so as we said, each hypothesis would correspond to a certain state. So those states that give the best correlation between the observed measurements and the predicted measurements are the ones who will gain in this weight. So we will increase the weights of those, we will decrease the weights of those states that give fallacious or wrong, predicted measurements. And by that, we'll just update the weights using this. And just remember, since we keep a logarithm of the weights, so this would turn into a simple addition instead of this product form, which could lead to round-off errors and, approximating most weights by 0. This is, of course, we will call this the update block. And now we're going to showcase the results. We are going to apply the algorithm to a fictitious map. So with the figure here, show us different things. First, now this map has been generated randomly between 0 and 1, okay? So I just generated several points and I just called them the landmarks. I kept them as a known matrix. Now the red dots are the landmarks. Now right here we can see that the robot has this pink type of circle. The robot starts here, and this is the robot sensing range. In this case, we can see that the robot can sense this landmark and this landmark. Now this blue one right here is actually the nominal path of the robot, which is to say the path that the robot would follow if there was no noise on the motion commands. This is the setting that we're going to work with. Now, this figure right here would show the same robot and the same sensing range. However, we show the real path of the robot, which is in black, and this one is the result of applying noise to the motion commands, and the blue one is actually the nominal path. Now this would just serve to show that if the robot only uses its odometry information, it's going to stray far away from the expected path, and that's why the Kalman filter, or in essence localization using measurements, is actually super important, because as you can see here, a small noise might cause a large deviation between the two trajectories. Alright, here we show the results of the filtering. Now the black one is the real path, the red one is the filtered path. We can see here that first of all the filter has no idea where it started. Now I should mention that I started the states, I scattered the states randomly between 0 and 1. And so in the first few steps, the filter has no idea where the robot is, and the mean of all of those, hypotheses give us two wrong estimations. But you can see as more and more measurements are incorporated, you can see that the filtered path closely follows the real path with really great accuracy, enhancing the accuracy over the just using the odometry, which gave us, terrible results. And now we can see also the angular estimation error, that is the error in the orientation estimation of the robot. We can see that, first of all, as usual, it started very high, and then in like 6 time steps, it just dropped significantly, maybe having a peak of up to 9 degrees and much less on the rest of the interval. So this serves to show that we are able to solve the EKF, the localization problem, using the extended Kalman filter. Of course, we're talking about the global localization. The kidnapped robot problem cannot be solved using this algorithm. Now, some final thoughts that I could add to this video. Now, some ideas that we could explore. We could try other types of filters, and I'm probably most likely going to try all of those. That is the particle filter, the Markov, and the unscented Kalman filter. It's usually important to say that the UKF and EKF usually have comparable performance. We might not notice that much of an enhancement using the UKF, but it's usually more used. There's also the Q-Batcher Kalman filter. It's kind of a variant of the UKF that is also like quicker and could provide also some interesting results. The second area, we could use more sophisticated sensor models. You could notice that in our case, the sensor model was actually quite easy. Although the measurements actually had noise on them, it was just, simple noise, just, simple additive Gaussian noise. Some other phenomenon that could be actually seen in real sensors, it could be misdetections. That is, I could have a landmark within the sensing range and I could just miss it all at once. Or I could just generate some measurements of things that are not even within the sensing range. Now, these two could be also handled with a more robust ideas. Of course, there's also the really interesting and newly emerging idea of using random finite sets. Now, this formulation is actually used to model the measurements. It's actually quite robust and quite powerful. It is to say in simple terms that we, represent the measurements as a set with a varying number of elements, or with a random number of elements and random components. And this could give us more advanced filters that could be used to to take those phenomena discussed in the previous point into consideration. And surely we have to relax the known data assignment assumption, because in the real case this might not be available. We might not know which landmark generated which measurement. Now this will be another video which will come out really soon. And that's it. Thank you very much for listening. And as usual, if you have any comments, any ideas, any recommendations on the qualities of the videos, on the method used, or if you have any suggestions of any other types of software I could use to, to give higher qualities of videos, I'll be super delighted to, engage with you in the comment section. And yeah, that's it. Thank you again.